So we've already been talking about different kinds of factoring. I'm going to go through a review of perfect squared trinomials. So a perfect squared trinomial will look like this visually, and then I'll show you what it becomes like as an equation. So suppose I have this nice perfect square. Now, a square is something that's like a rectangle, but it has sides that are congruent. So we know that this side length is the same as that side length. Let's pretend we know that this top length is ax plus b. If it's a square, this vertical length here will be also ax plus b. Let's go ahead and multiply and find what that area will actually be. Ax times ax is a squared x squared. Ax times b is plus abx. Ax times b is again plus abx. And finally, plus b squared. Notice that these two boxes are the exact same thing. So what I have here can be written like this. What I've been talking about is ax plus b squared. Again, that means times itself. That's what we did here. This became a squared x squared plus, notice these two boxes are the exact same thing. So I have 2abx plus b squared. This is the pattern of perfect square trinomials. The important things that you're looking for is that when you have a polynomial that looks like this, what you're checking for is the very first term a perfect square? Is the very last term a perfect square? Is this sign here positive? And then the middle term, what we typically call the b value, but in this case is 2 times a times b. If that relationship holds, then you do have a perfect square trinomial, which can be factored like that. If we have this with a minus sign, so ax minus b squared, the only thing that changes is the middle sign right here. So a squared x squared minus 2abx plus b squared. And you can prove that to yourself by plugging it straight into here. That'd be a minus sign, that would be a minus sign. The only things affected are here and there, because to get this far bottom corner, minus times minus is positive anyway. This final term will always be positive. So let's go ahead and take a look at an example. So looking at number 1 here, I'm going to do this with 9k squared plus 12k plus 4. First thing to check for, notice that 9 is a perfect square, 4 is a perfect square. The square root of 9 is 3. The square root of 4 is 2. 3 times 2 is 6, and 6 times 2 is 12. So what that tells us again is that if I'm making notes here, my notes are that this thing here is 3 squared. This thing here is 2 squared. And again, this middle part, I'm doing 2 times 3 times 2, which perfectly matches my pattern right here. So my end answer is 3x plus 2 squared. Now, you are welcome to factor like normal. I am only showing the shortcut here. If you want to factor the long way, you would do 9 times 4 to get you 36. Find two numbers that multiply to get you 36, and sum to get you 12. Factor by grouping all the way down. You will still get this as your end answer. But I'm not going to show that method here. You can go back and look at the previous 2 videos if you'd like that one. Let's do a second example. Let's do 25x squared minus 20x plus 4. And this one, I'm going to go ahead and color code a little bit better. Notice that this first term here is 5 squared. Notice that this last one here is 2 squared. Notice that in the middle here, I have 2 times 5 and times 2. So I'm color coding them black, red, and green. Okay, so this 2 is from the formula. This 5 is from here. This 2 is from there. 2 times 2 is 4, times 5 is that 20. So to go ahead and factor this, because that's a minus sign, just like here, I'm going to be using a minus sign in the middle. I'm going to have 5x, and at the very end, I have a 2. Now I just realized I made a mistake back here. That was an x. It should have been a k. Let me go ahead and make it back looking k-like again. I just changed my variables on accident. So this k here are the k's that I see right there. Take a look at a third example. Slide this one on up. For this third one, we have x squared plus 6x plus 9. Notice that automatically in front of the x squared, we have a 1, and the square root of 1 is just 1. So again, what I have here, number-wise, that's a 1 squared. In terms of this one right here, 9 is my 3 squared. And notice that in the very middle, that b term, it can be thought of as 2 times 1 times 3. Again, I'm saying 2 times first times last. So going ahead and dropping them into the pattern, I have 1x. I had a plus sign, so I keep the plus sign, 3. Go ahead and square it. And everything we found there, those are our final answers. So here's a final answer, and this one, and that one. And again, you do this if they've asked you to simply factor it. So again, perfect square trinomial, use it when the first term is a perfect square, last term is a perfect square, middle is 2 times first times last, and that final sign is positive. If it's negative, you cannot use this shortcut. To check your work, you can always go ahead and make that box grid or expand using FOIL. When you multiply them on out, you should always get back to whatever equation you were told to start with. Take a look at the sum and difference of squares pattern. So I'm still going to talk about this in terms of a square. This time, let's say that instead of the top and the vertical being the exact same thing, let's say they're off by a sign. So let's say I have ax plus b, and then I have ax minus b. That is an x here. Let's go ahead and find that area. So ax times ax is a squared, x squared. Over here, I'm going to have positive abx. Down here, negative abx. Finally, minus b squared. Let's go ahead and combine those like terms. So before I do that, let me make a note of what I just did. We just did ax plus b times ax minus b. And what we got was a squared x squared, positive abx minus abx, they're gone now, minus b squared is all that remains. This is the pattern we're looking for. First term is a perfect square, then a minus sign, then a pure number term, in our case, which is also a perfect square. So no middle term and no term that we normally call b. That middle term is just non-existent. Pure number, number and x. Let's go ahead and take a look at an example. Suppose I have 4x squared minus 9. Move that mouse out of the way. So 4x squared minus 9. Notice that my first term is a perfect square because this is the same thing as 2 squared. My last term is a perfect square because this is the same thing as 3 squared. I have no middle term, but I do have a minus sign. So I'm going to go ahead and square the end answer. We know that, actually, let me go ahead and change that. Sorry, mixing up my things here. There's no exponent, just parentheses. That's a mistake. So we're going to go ahead here and say 2x and 2x. Again, that's the ax and the ax. One of these will be positive. One of these will be negative. And that last value, let me use green to be consistent, is that 3 and that 3. So I should say 2x plus 3, 2x minus 3. There is no exponent. Again, that up there was a mistake. 2x plus 3, 2x minus 3. Let's go ahead and take a look at another one. Let's do 25x squared minus 64. Okay, so coming through here, we know that 25 is the same thing as 5 squared. 64 can be rewritten as 8 squared. We have a minus sign and no middle term. So go ahead and set up our two sections. Again, parenthesis times parenthesis. One of these will be positive. One of these will be negative. I have 5x going to be plus 8. I'm going to have 5x minus 8. And that is your final answer. Let's go ahead and do one more here. For this one, let's take a look at x squared minus 144. So notice in this one that this is 1 squared. This one here is 12 squared. So go ahead and put them into our pattern. Parenthesis times parenthesis. We're going to have x. It's going to be x plus 12. It's going to be x minus 12. So x plus 12, x minus 12. And that's your sum and difference of squares. The sum and difference of squares pattern is also used in other things, such as when you are working with polynomials and you notice that you have an irrational root or a complex root, its conjugate will also be present, which will have the same pattern as sum and difference. Again, if I have a 1 here, the 1 is still present. Any other numbers I have, take the square roots, put those in as well. Parenthesis times parenthesis for all of these. You can always go back and check your work by making yourself the box and multiply it out. Whatever you do, you must get back to what you started with, otherwise some mistake happened along the way. This next type is called the sum and difference of cubes. So if I have no middle term, purely number cubed, x cubed, plus or minus some other number cubed in my example, this is how it's going to factor. Now, what this means is that the first part of this is going to be exactly the same thing you started with here, just the cube roots of those numbers. So let's say that was 27, you'd use a 3. Let's say that was an 8, you would use a 2. Whatever sign you have here, use the same sign here. In the next parenthesis, take the squared version. So if this was a 3, this is a 9. Now notice here, I have minus over plus. It's upside down from here. What that means is use the opposite sign. If this one's a plus, this one is a minus. If that's a minus, this one's a plus. So basically whatever you had here, reverse it for the one in the middle. ABX says take everything here, multiply them together. Always end with the positive version of that last number squared. So that's simply a pattern to use. Know that if you have a hard time remembering the formula, you can always backtrack it. Know this part. Know that this will always go into this. So what you see here, this will always go into it. You can use long division to derive this part of the formula, and you can do that every time if you need to, as long as you know how to write it back into factored form. So let me go and give an example of what I'm talking about here. Let's say I'm starting with x cubed plus 27. That's a perfect cube. That's a perfect cube. So in terms of this one is 1 cubed. This one is 3 cubed. So to set it up, I'm going to have 1x plus 3. So just x plus 3. That's the first part here. But the second part, I'm going to go ahead and do that first one squared. Well, 1 squared is still 1. So 1x squared. Now I change the sign. This was a plus, so I'm now using a minus. And then multiply these together. 3 times x is 3x. I finally add that last term squared. 3 squared is 9. So that's how we factor that. Now again, if you can't remember the formula for this last part, you can always use long division, divide this by x plus 3, and you will be left with that. That is a perfectly valid option. Go ahead and block this off and put up another example. Let's say that I have 125 x cubed minus 1. Okay, well, 125, that's going to be 5 cubed. The 1 is just going to be 1 cubed. Let's go ahead and put them together now. So I'm going to take this one. I'm going to have 5x, keep the same sign, so minus 1. In the next set, take this and square it. 25x squared. This was a minus, so I'm now using a plus. And I have first times last, so 5x, and then finally end with this term squared, plus 1. And go ahead and block that off. I'm going to give you 2 more examples for this type. Let's come down here. For 3, we're going to have 216 x cubed minus 64. Again, notice here, 216 is a perfect cube. It is going to be 6 cubed. And 64 is also a perfect cube. It is 4 cubed. So I'm going to have 6x minus 4. In the next set, square this. So 36x squared. Flip the sign. Positive. The middle term is first times last. 24x. Finally, positive version of that last term squared. So notice that the last term is always positive. And let's go ahead and do one more here. So I'm going to do 27x cubed plus 8. And notice that 27 becomes 3 cubed. 8 is 2 cubed. So I'm going to have 3x positive 2, so plus 2. First set squared, 9x squared. Change the sign to a minus. First times last, 6x. Last term squared, plus 4. And you can use this pattern no matter what you have, as long as you only have 2 actual values. First term cubed, last term also cubed. It will always break down to this. And again, if you forget that end pattern, you can always take this, divide it by that. So again, notice that the cube root of these values, that is how you get that initial set of parentheses. If you divide the original by that set of parentheses, that binomial, you can always get out the end part, meaning that you are open to using long division or synthetic division. This last type I'm showing is called quadratic form. So what this means is that I'm going to have some sort of quadratic term hiding inside a polynomial that I can use normal factoring methods on. So let me give an example here. Let's say I have x to the 8th plus 5x to the 4 minus 14. Okay. If this had been x squared and x, we could factor this thing straight away. Now notice that it actually has a quadratic form to it. notice that if I'm talking about x squared and then x, that the x squared is just the middle term squared. Well, that same pattern is hiding here, and I can rewrite it to show that. X to the 8 is the same thing as this middle term, x to the 4, squared. That's by exponent rules. Power to a power multiplies. 4 times 2 is still 8. So plus 5x to the 4 minus 14. So again, what I want you to see here is that this term here is the same as that term right there. I'm going to use something which I'm going to call a U substitution. You can choose to do it this way or not. If you recognize this pattern, you don't have to do the substitution, but it typically makes it a little bit easier to keep track of. I'm going to say, let U equal that middle term, x to the 4. I'm going to substitute this in, so what I really have here is U squared plus 5U minus 14. Because again, from here, I know how to factor that. This first term is just 1, so A times C. Actually, let me switch colors here. I know that A times C is 1 times negative 14, which is just negative 14. I need to find two values that multiply to get me negative 14, but sum to get me 5. Well, if I look at that, I know I can use 7 and 2. So I'm going to go ahead and break that down. I'll be using 7 and 2. Notice I have to get a negative, which means one of these has to be negative. Because my goal is to get a positive 5, the negative is going to go on the 2. Notice that we get to use an extra shortcut here because this front value is purely 1. The A value in this case is 1. Remember, when we have that, we can plug these straight in. U plus 7, U minus 2. If this was anything besides 1, then we would have to use factoring by grouping or some other method. Now, I'm not quite done yet, and that's because U is really x to the 4. So let's go ahead and rewrite this as x to the 4th plus 7 times x to the 4th minus 2. That is our final answer. We have factored it as far as we can. Notice that we can't go any farther because this term here is not a perfect square. We are done. Let's go ahead and try this for another question. So for our second question, let's do x to the 6th minus x cubed minus 6. I'm going to make the same note as before. This, if I square this term, I will get to here. So let's rewrite that to show that part. X cubed squared minus x cubed minus 6. Again, what I'm showing here is that this term here is the same as that term there, and that's happening because this squared is that. It's just using exponent properties. Let U be that middle term, x cubed. Go ahead and replace it now. U squared minus U minus 6. Now again, I'm using this method because I realized that if this is a minus 1 and that's a minus 6, I can factor that. Notice that A times C is negative 6. When I break that down, if I choose 2 and 3, if I make that negative go on the 3, well, 2 times negative 3 is my negative 6. 2 minus 3 is my negative 1. That's how I know I've picked the right values. Again, in this case, my front value is just a regular 1, so I can use my shortcut. I'm going to have U plus 2 and U minus 3. I am not done yet because I'm going to go ahead and back sub this into there. So I'm going to have x cubed plus 2, x cubed minus 3. I check them. I do not have the sum and difference of cubes here, so I can go ahead and mark this off. That is my end answer. Let's go ahead and do another quadratic form. So here is question 3. we'll be doing x to the 6th plus 8x cubed minus 9. Notice again that I can rewrite this as x cubed squared plus 8x cubed minus 9. Again, my reasoning being this term is that term. I'm going to be using those special exponent properties. So I'm going to have u be that middle term of x cubed. When I do that u substitution, I'm always having u be equal to that middle amount of variable. X cubed, x to the 4th, whatever it is, have u be that value. Because when I plug it in, u squared plus 8u minus 9, this is now a quadratic that I can factor. So, same process as before. Find a times c. 1 times negative 9 is negative 9. I begin to break it down. I need something that gives me a multiplication to negative 9, but a sum to 8. I will be using 1 and 9. Notice that I must get them to be negative 9, but positive 8. So I'm going to use a positive 9 and that negative 1. Again, because negative 1 plus 9 is that 8. So again, that's the reasoning I'm looking at. Okay, let's go ahead and plug that in then. U minus 1, and I have u plus 9. Okay, go ahead and substitute our values in. X cubed minus 1, x cubed plus 9. This time, though, we are not done yet. This here is a difference of cubes. Let's work just on that for a moment. So notice that this one here is 1 cubed, and this one here is also 1 cubed. So using our special patterning, we're going to have 1x, keep the sign, minus 1. The second set, take this and square it, x squared, flip the sign, multiply together, add that last term squared. So this stuff in blue is equivalent to x cubed minus 1. And then go ahead and drop down x cubed plus 9. That is the answer in fully factored form. Okay, let's go ahead and do one final question. So looking at 4, we're going to do 3x to the 6th plus 16x cubed minus 12. And notice that I have x cubed, I have x to the 6th. Let's go ahead and rewrite that. So 3x cubed squared plus 16x cubed minus 12. Again, what I've noted is that that x cubed and that x cubed are present. I'm going to let u equal x cubed. So when I rewrite this, I have 3u squared plus 16u minus 12. Now, I'm going to go ahead and begin to factor that. Now again, sometimes it won't actually work. It won't always factor. The stuff I'm giving you here is definitely designed to factor. So let's start with a times c. This time, you do have an a value. 3 times negative 12. Make a note of that. That gets us negative 36. So your job is to find two numbers that multiply to get you negative 36, but sum to get you 16. So let's go ahead and look at our possibilities. I have 1 and 36. Not going to work. I have 2 and 9. Oh, whoops, that's wrong. Sorry. 2 and 18. 2 times 18 is 36. And also notice that these have a gap of 16. The question now becomes, which one is positive, which is negative? This 16 is positive, so my bigger number 18 must be positive. Have 2 be the negative. Add them together to prove this does get you out negative 16, and that's why we're going to be using this when we plug stuff in. Now, unlike the other ones in this quadratic form section, notice that I have a 3 here. I can't directly plug them in like I did up above. I'm going to have to factor by grouping. So I have 3u squared minus 2u plus 18u minus 12. And again, I showed factor by grouping in my 2 first factoring videos. Factor the first 2, factor the last 2. I'm going to take a u out of both things here. So basically come through, divide by u. What you're left with is 3u minus 2. Do the same thing over here. This time, they both have a 6 in common. I'm going to pull out a 6, divide that by 6, divide that by 6. 18 divided by 6 is 3, so 3, and then a u, divide this, and I get negative 2. And again, that's what I'm hoping for. I want these insides to be the same. I'm now going to factor those insides out of this. I have 3u minus 2. What I'm left with is u plus 6. Again, if I take it out of here, I'm left with a u. Take it out of here, I'm left with a 6. Go back to the beginning and do our plug-in. Remember, u is really x cubed. So I have 3 x cubed minus 2, quantity, x cubed plus 6. The remaining stuff here are not perfect cubes, so I am done. This cannot be factored any farther. There's nothing left in common. Okay, so this video has covered quadratic form, sum and difference of cubes, sum and difference of squares, as well as perfect square trinomials.